Hello, and welcome to today's American Nuclear Society event featuring an update on Project Pele. I'm Alex Gilbert, Director of Space and Planetary Regulation for Xeno Power Systems. I'll be serving as the moderator for this discussion today. Before we get started, I'd like to cover a couple of quick notes regarding today's event. If you have any questions, please type them into the Q&A function. I will attempt to address as many of these questions as possible. The event will be recorded, and a link to the recording will be emailed to event registrants later on today. Additionally, certificates of attendance for today's event are available by request. Please see the chat for contact information. And finally, we ask that all participants adhere to the ANS Code of Ethics and Respectful Behavior Policy, which can be found at ans.org. So with those notes out of the way, I'd like to go ahead and introduce today's featured speakers. We have Jeff Waxman and Joe Miller. More details about their bios can be found in the chat. But first, I will turn it over to Jeff Waxman for an initial update on Project Pele. Jeff is the Program Manager of Project Pele in the Strategic Capabilities Office within the Office of the Secretary of Defense. And Jeff, I will turn it over to you.
So I'll try to be relatively quick because I know we've only got an hour and I want to get to the Q&A. But Project Pele is a transportable nuclear reactor. It's being done in the Department of Defense. It is a set of 20-foot Conex boxes. It will produce between 1 to 5 megawatts of electrical power. We had a design competition. We started in March of 2020. We started with 3 companies. We down selected to 1, so that's BWXT. What we are in now is the final bits of the design phase, all the last little bits that we have to do to get to final approval of the reactor by the Department of Energy, who's our regulator. Our current schedule is that we hope to have the design approved by the Department of Energy. It's the final design approved by Department of Energy by the spring. So as part of that, we are now ordering hardware. We are making fuel. We are forging the containment vessel. We're making moderator blocks, all that good stuff. We have now reached the point in the famous Admiral Rickover essay where we are no longer a paper reactor. We're an academic reactor. We are now becoming very real. And so the goal is that by the spring, if the Department of Energy has signed off on the design, we will start to assemble the reactor with the components that will have arrived in Lynchburg. The reactor will then be assembled over the course of 2024. If all goes according to schedule, by early 2025, we will have shipped the reactor to Idaho National Laboratory. At Idaho, it will then be fueled. It will then be shipped out to the desert to a location that we have selected to do the initial testing. The reactor will then go through a final operational readiness review. And if all, again, goes according to the schedule we have right now, we will be able to turn the reactor on before the end of calendar year 2025. After we operate the reactor, we will then demonstrate that it's a transportable reactor by tearing the reactor down, putting it on a truck, driving it around a bit, setting it back up again, and turning it back on again. So this is a reactor, to be clear, that for DoD purposes is focused on really largely 3 types of applications. It's focused on remote power, so places where it's very difficult to get power. Islanded power, again, places where it's difficult to get power, but also reconstitution. So we are focused on offsetting fossil fuels for 2 main reasons. One is for climate purposes. The DoD is trying to get off of fossil fuels and move to net zero, but also from a strategic and operational perspective, our resilience on long and vulnerable fossil fuel lines is a huge problem from a military perspective. So having power that does not require refueling for days or months or even years would be a huge advantage. So as I mentioned before, the company that is building the reactor for us is BWXT. I think now would be a good time for you to turn over to Joe Miller so you could talk a bit about what BWXT is doing and is going to be doing in the future. Thank you.
Okay, thanks so much for that introduction, Jeff. So Joe Miller is the president of BWXT Advanced Technologies, leading a team delivering the Project Pele Advanced High Temperature Gas Reactor Power System, the Draco Nuclear Thermal Propulsion Reactor, and the commercial BANR reactor systems. His team also performs development for NASA's Fission Surface Power Reactor and a variety of other research and development in BWXT's nuclear laboratory. Joe, turn it over to you.
Excellent. Thank you, Alex, and thank you, Jeff. And Jeff, you laid out the program quite well, and making this reactor real is exactly what I'm excited about. We've gone through the design competition. we understand to a really, really in the weeds level of detail the entire design, all the attributes of that design that needs to be manufactured. And over the last couple of years, we have been employing this design, build, test methodology that was so fruitful in the early days of nuclear, and we've been re-employing that. And within BWXT, having a design to manufacturing capability is something that we've sustained over the last 6 or 7 decades through a variety of different programs. And being able to apply it to a first of a kind high temperature gas reactor that is an advanced reactor, and all of the attributes of this system, not just BWXT, but also our partners in Northrop Grumman, our partner in Rolls-Royce Liberty Works, being able to work with that strong team, being able to work with Idaho National Lab, and then the Strategic Capabilities Office as a collaborative team to make this reactor real has been extremely rewarding to date. And we're really excited about the components that we've been procuring, the assembly sequence that's starting to take place, integrating each one of the components for the reactor, and then integrating all those Connex boxes that Jeff mentioned. So completing that system, going through commissioning, and eventually critical testing and the full suite of tests that are required by the program is just an exciting next couple of years. So using all of the attributes and capabilities within BWXT and our partners to be able to make this the pathfinder advanced reactor for the country and really for the world to look at things like important tactical purposes for the Department of Defense, and then also how microreactors can help decarbonize the grid is just an exciting time to be part of nuclear, and really happy that that we're here today talking about the program. All right, back over to you, Alex.
Thanks for that, Joe. Jeff, if you want to join us. So I went ahead and I prepared several questions. We also got some questions ahead of time, so I'll go ahead and start through those. But please, if you do have any questions, go ahead and put them in the Q&A function and we will get to them as we can. So to start off, this is one of many project themes where the DoD is looking to the commercial sector. What is the value here of the Department of Defense sourcing these type of reactors with their commercial partners? And how does this fit into the broader picture of commercialization efforts for advanced reactors for either panelist?
Well, I would say that there's a long history of the DoD developing technology that then becomes commercialized. You know, there's famous examples like, you know, the internet and GPS, but there are many others. And nuclear power is actually a perfect example. I often give the example that the first commercial nuclear reactor ever built in the world in Shippingport, Pennsylvania, was built by the Navy, and it was an aircraft carrier reactor design. And so that allowed the commercial companies to see a design, to see something that worked, to understand the manufacturing process and go and run with it from there. So our plan from the start of Project Pele has always been that we want to build reactors that can have commercial spin-offs so that we can get the number of reactors coming off the assembly line to be enough that it'll be cost competitive.
Yeah, and you can see that, just to add on to that from a BWXT-centric point of view, for what we've been doing in Pele as a high temperature gas reactor, we've been able to parallel some of the activities within BWXT for our Banner reactor. So having the capability and the understanding and the supply chain knowledge and all the design for manufacturing effort that's gone into this program, we're able to port that for commercial purposes and looking to how we can apply that commercial reactor to future markets.
And then for Jeff specifically, one thing that I think comes up very often with this discussion is the question of safety for a microreactor like this, especially for Defense Department applications. I know that you all have done a fair amount of work on that. Would you kind of be able to talk through some of the safety analysis that you've done, how the authorization process is going, any major updates there?
So from just a reactor safety perspective, so leaving aside the kinetics for a second, which I guess we can get into later maybe, but we are choosing to have this reactor regulated by the Department of Energy. So it's the Department of Energy that is approving the design. They are also this final sign off before we could turn anything on in our operating plan, and they also regulate the operators. That said, we're making this reactor to be what we call NRC certifiable. So while the NRC is not licensing the reactor, the NRC does sit on all of our design reviews. They have the opportunity to express any input that they may have. We're also working with the NRC on over-the-road transport. We would like to be able to, if asked, to be able to drive this reactor on public highways after it's been operated. And so we've been having a bunch of work with the NRC to develop that pathway as well. In fact, if people really want to be in the weeds, we had an NRC public meeting not that long ago about this very topic. So while this initial reactor is being regulated by the DOE, we are trying to be flexible based on the way that the Department of Defense Services might want to do things in the future.
Joe, anything to add on that, especially as it comes to some of the more novel features with NRC?
Yeah, well, packaging the design information into a licensing document is a skill, right? And we're flexing that muscle with the DOE authorization basis. There's a slightly different way to do that with the NRC, but giving the Nuclear Regulatory Commission the ability to watch this program and start to prepare themselves for high temperature gas reactors and other advanced reactors, I think has been a benefit for the country. And so it's a way to package it. It's a way to communicate, early and often, and credible communications are really important. So we have that focus, especially with our commercial reactor program.
And where's the fuel coming for this, both in terms of fabrication, enrichment, and is this an area where we can see this kind of as a trailblazer for future efforts on the supply chain development in the US?
So in terms of the actual uranium itself, we're getting that from an NNSA stockpile. We're using some old HEU that was not being used by anybody else. So that's all coming out of stockpile. It actually comes out of some old nuclear warheads that were decommissioned in the 90s. In terms of actually taking that fuel and down blending it to HALEU and then turning it into TRISO, that's all being done by BWXT at their Lynchburg facility. So we worked with NASA and Department of Energy jointly to take BWXT's laboratory scale TRISO line and scale it up to both commercial scale, but we are also working to expand the types of TRISO that they can make on the line. So while Pele will only be using the standard AGR variant of TRISO, that line will be able to produce a wider variety of things. And Joe, I'm not sure if you want to add anything to that.
No, that was really well said. That would be the Pathfinder, right? We have an industrial scale TRISO capability here in BWXT that's capable to make all the fuel required for Pele and additional units. We've also, in our coated fuel capability, in that same facility, we've manufactured coated fuels for NASA. We're doing the same thing for the specific TRISO fuel that we are developing for our Banner reactor as well. So that would be the Pathfinder. You flex that muscle between the enriched uranium all the way through a product, a compacted TRISO, and then use that in a reactor. So there's other elements that have to be developed, but it's definitely a huge first step.
And both of you mentioned NASA, and I think it is really worth shouting out the news last week. We're really excited to hear about the Draco award to BWXT to develop a nuclear thermal propulsion system for outer space. And I know that you at BWXT have been working a lot on that. But I know that, Jeff, you've also, I believe, been doing some coordination. Heard you talking at NETS a couple months ago. Would the two of you be able to talk a little bit about kind of some of the synergies or the benefits or perhaps the lessons learned for Draco from what Pele has been able to accomplish so far?
Sure. So yeah, we certainly work very closely with the DARPA team. For a while, SCO was actually in the DARPA building. DARPA since kicked us out, so we're now in a different part of town. But I certainly know Tabitha Dodson very well, and there's a lot of overlap in large part just with our teams. Tabitha has supported us. I've supported her. And a number of the laboratory people who I work with have been kind of lent to Tabitha to help her with that. And certainly, I'm sure Joe could talk to the synergies on the BWXT side. Obviously, there are several differences with the space reactor in terms of, it's just an NTP system. So it's not nuclear electric, but also the way you cool reactors are very different in space. But I'm a big believer that the hard part of nuclear engineering is really not those larger details. It's really the smaller details. How do you make real things real? And so in that way, there is just a ton of overlap between Pele and Draco. And Joe could probably talk to that better than me, since these are both in your organization.
Yeah, that's right. Yeah, we were excited as well. It's another important step forward for nuclear, now space nuclear, for the country. And being a participant in leading those programs from the industry perspective, I think the pathway from NASA NTP starting in 2017, the Strategic Capabilities Office JEFS program starting a few years later, and then NASA and DARPA having an interagency agreement to go off and demonstrate space nuclear, noting that the way to demonstrate space nuclear, especially thermal propulsion, is in space because we don't have the facilities. The licensing becomes an unknown. And so just think about the breadth of government involvement that now exists that didn't exist just a few years ago. That's an amazing feat all by itself. And the fact that the government's coming together, especially co-funding Draco, and then having a lot of internal government discussions that I'm sure Jeff is a part of, is just another way for everybody in the American Nuclear Society to feel really comfortable that this emergence of new nuclear is from the commercial, it's from the government application, it's space application, and it's injecting a lot of excitement into nuclear writ large. As far as the technologies go, there are similarities, right? So the reactors are different. They use uranium-235. That's a big similarity. The rest of the materials are quite different. The geometries are quite different. But the way in which you control a reactor is similar, regardless of the reactor. And then the fuel manufacturing capability can be pretty flexible. So being able to port one type of fuel manufacturing equipment and laydown area and things like that offers a big benefit. And then the control systems that go along with nuclear reactors have a lot of similarities. So, being able to tie those similarities together, being able to use, my staff is super excited because they get to work on a mobile reactor and a space reactor, as a matrix entity. So it's all good stuff. But I think the fact that the government is putting up real money to build prototypes to demonstrate new nuclear is something we haven't seen in a very, very long time. So having 2 prototypes out there that the government's been sponsoring is injecting, a lot of vitality back into nuclear, and it's just great to be part of it.
I'd agree, Joe, that I think we are really seeing a competitive ecosystem emerging for the first time in a long time in the US, and it's a very exciting time. One thing I did want to follow up on, Joe, is specifically the idea of manufacturing lines for reactors, and especially with Pele. Yes, we're a demonstration project right now, but BWXT does have a lot of experience with these type of manufacturing lines. And if we are to be successful in this new era of nuclear, we're going to have to produce a lot of these systems. So any general observations just from BWXT's experience on how we're going to be able to leverage manufacturing and fabrication to get to where we want to go?
Yeah, it's a couple of different focus areas that we've had internally. The company, BWXT, has invested a lot of capital in making facilities available for the prototyping. So we have our innovation campus, and over the course of the last 5 years, we've transformed even our organization. We've transformed our footprint here in Lynchburg. We had about 10,000 square feet to do early R&D. We're finishing the renovation on a 170,000 square foot building that will have those 2 prototypes, both Draco and Pele, and inside. So we'll do a lot of cold commissioning. We'll do a lot of early testing, and then the fuel will be made nearby here, also in Lynchburg. But so I think low rate production is the next step after prototyping. So that 170,000 square foot building is there for that. We've really been sharpening our skill set on translating from design to prototype. So that manufacturing feedback loop that we've established over the last couple of years in advanced technologies is really pulling on a lot of resources and a lot of know-how that exists within our company. So if you think about it from high throughput manufacturing as the final step, so prototype, low rate production, that all can happen in the footprint that we're finalizing now. High throughput manufacturing is going to be extremely important, right? And so I'm lucky enough to have that in my background. I worked in semiconductor manufacturing for 6 years, and nothing's more high throughput and high quality than semiconductors that I've ever seen. So taking those lessons learned, taking lessons learned from other industries like automotive or pharmaceuticals that have high consequence, and being able to create a more robust supply chain for nuclear, where you're doing more integration, more assembly than just hands-on manufacturing in a single location is going to be really important. So the way that I see it is we'll be able to function over the next several years in prototypes and low rate production, what we have here. But then my eyes are really set on what does that factory of the future look like? So a lot of the R&D that we have in advanced technologies now is focused on that. What type of automation sequence, inspection sequence, QC, all the things that are really important in delivery. Preparing for that so we can meet that demand when it shows up is going to be important, and that drives down cost. That's the important thing here. These reactors have to be cost effective, and you have to have that pretty early return on the investment from the customer side too. So it's pretty unique right now because there has never been a high throughput reactor manufacturing facility in the U.S. And so we want to drive to that as well, so we can prove to our future customers that we can make these reliable, we can reliably, be able to hit all of our overall delivery targets, and then make them very, very cost affordable is a focus for us.
Thanks for that, Joe. A lot of insight there. One final of the questions from before we got to the webinar, and then we'll turn to the Q&A questions. So I think, Jeff, I really appreciate your comment in the intro about the paper reactors and how this is really moving to one of those real reactors. And you all are working on actually fabricating a reactor right now. And 2025 is really right around the corner in the reactor world. As you're going through this process right now, you're actually doing it. Are there any sort of lessons learned, surprise roadblocks, things that were easier than you expected, things that as the broader industry is starting to get back into this building phase, we should be keeping in mind both for some of these demonstration reactors, but also just for nuclear technologies more generally?
I wouldn't say anything is easier than expected. I think the lesson from Admiral Rickover is that everything is a little bit harder than you think it is. And there's just a lot of lessons learned, I would say, in general. One of the things that both we've been doing on our side, and we've asked BWXT to do as well, is to write down lessons learned, because there's just a few things that you wouldn't even think about that turn out to be kind of important. And we can't get into too many of them here. I would just emphasize that I came from the space world before I was here. I worked at NASA for a little while, and one of the things that often gets talked about space companies is about, are you have a lot of hardware or a little bit of hardware? If you have a lot of people on computers and very little hardware, those space companies generally make less progress than the ones who have a lot of hardware and just let people tinker and learn. And so hardware is so crucial. If a nuclear company is going to be real, they have got to have hardware on the floor. They've got to be learning. They've got to be making mistakes, and that's the only way you're going to get anywhere. So I can't get into any real details beyond that, other than to just say that there's nothing that's easier than you think it is. Most things are harder than you think it is. I have to say, I've been in, I was actually I think almost no one involved with this program anticipated how complicated it is to get regulatory approval on a nuclear reactor, even through the DOE, which is a easier process than the NRC. You have to consider, well, what if this goes wrong and there's an earthquake and there's a fire and all your computers go out? How do you make sure nothing bad happens? And that's why nuclear is so safe, is just because of this. So I appreciate it. I'm glad we're going through it, and it'll probably be a little faster when we do it the second time. Joe, do you want to add anything to my confusion?
No, that was well said. Actually, it was really well said. Being able to tinker is exactly why the design, build, test methodology works, right? And so having small test rigs, we've been building this reactor for 7 months now, right? And we've been doing it in surrogate materials because you have to understand that process. And just like Jeff said, being able to feed that back into the final design is really important. And so it's hard. It is really hard because a reactor, when it operates, isn't really all that complex, right? You have control mechanisms and you have some circulators. Everything else is pretty static. So the hard part is making sure you get it right in core physics, make sure those core physics are represented in what you actually deliver. So it's a lot of lessons learned so far. We expect a lot more, especially when we get into cold commissioning after integration. But yeah, it's been exciting, and being able to tinker is the name of the game right now, because when we build it and we ship it, it's got to be right.
Excellent, thanks. So there are a lot of really good questions in Q&A, and we'll try and get to all of them. So picking up on kind of a common thread, one thing that seems to be of interest is how you all will be planning on handling the spent nuclear fuel here, as well as potentially some of the other decommissioning of the system itself. I guess both for this project, and then also because if you could talk kind of generically about what are the outputs that you need to deal with from a waste perspective here.
Yeah, so one of the things that I can't necessarily speak for the Department of Defense and what they want to do, but I find it very unlikely that the Department of Defense will ever allow refueling or defueling out at its independent sites. I think that would be a nightmare from a regulatory perspective. So there are several reasons why we decided to build this reactor in a series of boxes rather than in one big box. But one of the advantages is that we have one reactor module that has the nuclear stuff in it, for lack of a more technical term. All the radioactive stuff is in one box. There are very few moving parts in that box. And the idea is that that box will be shut for the entire length of the operation. And then when you're done, you ship that whole box back and you get a whole new box. We do not want people opening up boxes and messing with used fuel at a remote military site. Now, in terms of what happens when you actually remove that fuel, for the first of a kind, we're just going to store it in temporary storage at Idaho. In terms of the long-term solution, I mean, we're just in terms of like Yakima and everything else, we're just Mongo, pawn, and big game of life here. We're not the ones who are going to drive this. The amount of nuclear material that we're using is so small that we could build 10 Peles a year and we'd still be a pretty small problem relative to the larger problem of what is the country going to do with its nuclear waste, which is really, as I think everyone on the line knows, a political problem, not an engineering problem. Joe, I don't know if you want to add to that.
No, I think you covered everything. It was really well said. And yeah, I like the idea from the very beginning on Pele to have that box and be a singular unit that you can replace as well. So you don't have to replace all 4 Connex boxes when you need to refuel. You essentially just ship one in and ship one out.
And in terms of the transportability of the reactor, it does seem to be kind of a prime feature of this ability to ship it to a potential war zone, a front operations area. Also, just for it seems like across the life cycle, being able to transport, and that is part of the demonstration itself. Can you talk a little bit about some of the any of the design or other policy challenges related to that transportation element, especially just because that is pretty novel compared to how we are normally dealing with any sort of transport of nuclear materials?
Yeah, that's a big question. I'll try to get to that as best I can. I would say first of all, in terms of putting this in a war zone, the DoD talks in terms of tactical zone versus strategic zone. And we do not anticipate putting these in the tactical zone. So to imagine like the Ukraine scenario now, I don't think it's likely anytime soon someone would allow a nuclear reactor on the battlefield in a place like Ukraine. That would probably be too dangerous. So what we're looking at is stuff that's many hundreds of miles, if not thousands of miles from where shooting happens. Now, that said, in the modern day, anywhere in the world can be attacked. If nothing else, there could be terrorist attacks, not to mention that there are missiles that could hit anywhere in the world. So we are very focused on trying to make sure that even in the worst case scenario, it is not a significant release. It's not well, the word significant means different things. There would be, you can imagine a scenario where you could break this thing and release radioactivity, but we're trying to minimize that as much as we can. From a legal perspective, there are several legal things you have to get through. One is, we talk about flying this thing on planes. That's a lot easier flying it out than flying it back because it's illegal in the United States to fly plutonium. And once you operate a reactor for even a few minutes, you're going to create minute amounts of plutonium. And how we deal with that is a policy problem that we're going to worry about in the future, I would say. For now, we're focused on taking used reactors back by truck if we have to. In terms of using these reactors anywhere that's not the contiguous 50 states, basically, this would fall under the sort of status of forces agreements that we already have, in the same way that the Navy, if they're going to port a ship in a country, they don't just show up at the country. They have an agreement in advance with that country laying out all the rules behind why a nuclear-powered ship can go there and what happens if things go wrong. And if there are certain countries or ports that do not want nuclear things in their port, then the Navy does not go there. So I think it would follow something like that. And it would also follow that way, to be clear, also on U.S. territories. So if you think about any of the islands in the Pacific or Puerto Rico, anything like that, those also would require the agreement of the local government. For those who know their nuclear history, back in the 1960s, the U.S. Army actually snuck a mobile nuclear reactor into Greenland underneath the ice without telling the Danish about it. And when Denmark found out several years later, they were not happy about it. And I just want to emphasize that in the 1960s, there were no laws. It was like Mad Max. In the 21st century, there's no way that we would even attempt to do something like that. We will not put nuclear reactors unless it's a place that wants those nuclear reactors to be there. Joe, I know you have Navy experience, so maybe you could add to that as well.
No, I think you covered everything, right? It's just part of the process, and there are plenty of applications right now that are low-hanging fruit for nuclear reactors and microreactors. So as this technology continues to develop and continues to gain acceptance, then I expect it to continue to push out into further and further regions.
There was a question about the requirements for operator training, qualification, and all of that. I know this is kind of a unique case, and especially looking at potential things like automation. Can you talk maybe a little bit about that, especially as it might relate to potential lessons learned for other types of autonomous reactors?
Yeah, so we anticipate this reactor is largely autonomous. That said, there's always going to be some need for operator input. And even if you had a fully autonomous reactor, I view it the same way that you look at autonomous cars. While technically we have cars that can drive themselves down the road, no one allows cars on the road without a driver at the steering wheel. And the same thing is going to be true of nuclear reactors. It will be a very long time before someone allows an unaccompanied operating nuclear reactor. I don't think that's going to happen anytime soon. So we are assuming that at all times there will need to be two operators, in the same way that if you fly a 737, those planes can fly themselves, but there's always two pilots. And in terms of what exactly that training looks like, we are currently working with Idaho National Laboratory as well as West Point and the Engineer School to sketch out what that training would look like. And also, and this is relevant for the commercial industry, Idaho National Laboratory has hired several people, mostly former naval reactor folks, who are their new cadre of operators. And these people will be trained to operate Pele. They will also be trained to operate Marvel. And they will then be available to operate other reactors that might come down the road in INL. So we're hoping to create an ecosystem of operators who are trained at handling different sorts of advanced reactors and knowing the basics of how to be a little bit creative and outside the box. So hopefully that will help not just Pele and Marvel, but also any other commercial company that in the future wants to come down the road and try out their prototypes at Idaho. They will hopefully get a leg up from that work that we've done.
Yeah, I'd also say the physics basis of a high temperature gas reactor in particular is pretty amenable to autonomous control or semi-autonomous control. So being able to collect that data during the operational sequence can help us build a case over time for more hands-off control of the reactor. So the general design of Pele is easily, I would say, transformed into semi-autonomous mode, and then, you know, once again, being able to get the operational data that's required to go beyond that will be available just because of the nature of where we stand on computational products that can be applied to the control system and to the data monitoring system.
And a question perhaps to start with you, Joe. There was a number of questions in the chat regarding the lessons learned and how they translate to the broader industry, especially commercially. I know we talked a little bit about that, but really I think, how do you kind of see this one project fitting in with kind of the broader things that are happening right now, and how can we leverage this so that the lessons learned right now, I think, really help jumpstart things for the nation?
Yeah, so I think you start with licensing, right? Being able to take all of the design information that's being created on a variety of different projects and having Pele as a very focused project, translating that design into a licensing document will create a tremendous amount of lessons learned. So that's on the licensing side. On the engineering side, once the unit is operational, the performance data that comes from that unit will help us make adjustments to what the design is, how the reactor is operated, how the entire system is balanced, and then incremental improvements, just like any other technology. And so there. And then I would also say, from a manufacturing standpoint, flexing that supply chain now has been a pretty big effort. It's not as daunting as maybe I would originally thought. I wouldn't call it easy, just like Jeff said. I wouldn't call anything on the program easy, but when you reach out to vendors and you talk about nuclear nowadays, even it's different than 2 or 3 years ago, right? They see what's happening in energy security. So a lot of the vendors are getting pretty excited about what the future may hold. So if we can couple the lessons learned from the licensing activity, from the technical design and performance of the reactor, and the supply chain, then I think those are 3 pretty big feats that haven't been created on a new reactor design in quite a long time. So there'll be lessons learned from each one of those avenues, and they'll be shared as appropriate. But I think it's flexing the muscle of nuclear, and that's always a good thing.
And I think this might be a little bit more for Jeff, but when you look at the potential applications of Pele in the future, when we look at the Navy, we've got the Naval Reactors Program. Previously, the Army has had a program to manage their own reactors. What does this look like from a programmatic side within the US government to actually use these reactors to go beyond SCO?
Yeah, so SCO is just a prototyping organization. So we are not an operational organization. So we can make one, but then it has to be transitioned to a service. There are two ways that services look at energy. They look at operational energy and installation energy. In a way, that delineation between operational and installation energy, I think, is a little bit old-fashioned, but that's just the way the Pentagon bureaucracy is set up. So when we talk about operational energy, that would go down one acquisition pathway versus installation would be another way. And so installations would be focused on providing reliable 24/7 power at domestic installations, places that need to have power 24/7. There are a number of places in the US where we either operate drones from or have crucial computers or satellite downlinks or other operation centers that need to be operating all the time. Now, for operational energy, that would be if we were talking about, say, islands in the Pacific, then that would go down the operations pathway, and that would be focused in a large way on things like radar systems, perhaps. Again, satellite downlinks is another key thing that they have to worry about over there. Reliable energy is it's a challenge. Literally yesterday, here's an anecdote. I was talking to some folks at a military installation in Puerto Rico, and halfway through the meeting, it cut out because they lost power for 3 hours. These are huge challenges that a lot of DoD installations go through. So I really think that in the short term, the applications for this will be largely on installations, and it'll be about just being able to provide that reliable power in case the grid goes down. Because right now, installations are just very vulnerable to losing power. And this is without a near-peer adversary using cyber attacks to try to keep your power out.
And I guess kind of maybe looking a little bit at the project development right now. So fabrication has started. It's targeting 2025. Are there any sort of major barriers or concerns that you have in kind of getting the reactor from now to operation? And how are you thinking about that from a risk mitigation or management perspective to get this on time, or at least close to 2025?
Yeah, I mean, there are a lot of issues that we're working through. We have a number of Tiger teams that are set up to deal with little problems. Most things are either related to being sure that you could handle these worst case failure scenarios, but also, and this is something I think a lot of people in startups maybe don't always think about, but it's making sure that every part of your system can handle high radiation environments for years at a time, and to make sure that you have the data that demonstrates that your system won't become, say, brittle or cracked or more likely to break, that you're not going to have common cause failures. This is a common mistake that people make in engineering, is to not think of, don't think of failure as individual instruments, think of common cause failures. But then we're also always concerned about supply chain. We know that one of the big things that caused delays in Vogtle was that their subcontractors could not deliver what they said they could deliver. And so we have, and BWXT in particular, if Joe wants to talk about this, have been very aggressive at trying to make sure that the companies that are making parts and components really can build things to the exact spec that we need them to. I'd say those are kind of the key risk mitigation areas that we're focused on.
Yeah, and there'll be things that'll pop up throughout the program, absolutely, as we continue to get more deliveries from our vendors. So keeping that close communication with those vendors, and like Jeff said, supporting the vendors to be able to deliver exactly what we need is going to be crucial. So it's just going to be a constant effort of communication and build, and there'll have to be adjudications along the way, but we feel like we're set up for it.
And so we did talk a little bit about the international deployment, I think really from an operational perspective, or maybe from a bilateral perspective. But I think when you look at this project, especially if we're going to be having many of these activities going on, the microreactors really are different than traditional systems we deployed. Have you thought about what types of nuclear security or safeguards needs might need to happen, and any comments on any sort of international standards or expectations to support a broader framework to address those?
Yeah, that's a complicated one. We've had a lot of conversations with the State Department and NSA and the White House on this, Part of it is just that this is a new gray area, that traditionally there was a very clear delineation for the IAEA between commercial power and military power, because military power just meant naval ships that, you know, that have weapons on them. And what happens if you have a nuclear reactor that is sitting on a domestic installation that is there to provide resilient power for a weapon system, but which is also tied into the commercial grid? Is that commercial power? If it's commercially owned, is that a military use? And so we kind of have to not be definitive there, because there just is some gray area on where military use is defined. Because from a safeguards perspective, traditionally, if you have a commercial reactor, then IAEA inspectors are welcome to just show up there and make sure that you're doing what you say you're doing, unless you're, you know, Iran and North Korea and you don't listen to them. But military reactors are their own separate thing, and the IAEA cannot just come in and inspect a ballistic missile submarine. And so where exactly we fall in there, this is actually really still a gray area and unresolved. And I'd say I didn't realize how many friends I would make in the State Department, or I'm not sure if they all consider it friends that we've given this extra work, but we definitely are working through this, and we understand that this will have to be a whole government decision and effort, because this is not just about safety for US reactors, but it's also about the tone and standard that you set for other countries. You want to make sure that we are not, you know, doing something that will encourage other countries to also evade IAEA safeguards. So it's a delicate, complicated issue, and I wish I had a better answer than that.
I think that makes a lot of sense. Definitely an area to be worked on. There's a number of questions in the chat just about the operations of the reactor in multiple locations. And I think especially when we look at things like environmental impact assessments, we've traditionally dealt with static environments that we have a lot of data or information on. Can you comment perhaps a little bit, either of you, about some of the challenges of thinking about a transportable reactor and how you do that licensing or that analysis for many different environments, and especially if we want to have the flexibility to move these things into new areas?
I would say that the trickiest part of environmental oversight for a transportable reactor is that it turns out that if you just, let's say you drop a nuclear reactor in the soil somewhere, and you want to understand, if I operate this reactor at X megawatts for Y years, and I remove it after 7 days, how radioactive is that soil underneath? It turns out that that's driven largely by very tiny impurities. It is not driven by the majority materials in the soil, and it's not going to be the same. You could be 1 mile apart and have 3 or 4 times the radioactivity after you leave. And so we've actually spent quite a bit of time trying to understand how we can model and how we can predict, with the idea that we don't want to have to do significant laboratory work every time we want to move the reactor. So this actually is one of the examples of things that turned out to be a little bit more complicated than we thought that would be, but I think we've got a pretty good handle at this point on being able to estimate the rates at which those impurities would be there. But the other thing to think about is that with a traditional reactor, you just put a bunch of concrete around it, and then when you're done, you just leave that concrete, or you just trash it. And in our case, we are not going to be building these big concrete domes, so we do have to worry about what happens outside. But we are getting a good practice run here, because where Pele is going to be prototyped is very sensitive cultural land of the Shoshone-Bannock tribes. So we had to make sure that it's not just that there are historical artifacts that have been found at that location, but also that drinking water to the reservation is nearby. So we've had a lot of interactions with the local community to make sure that hey, if we put it over here or we put it a couple hundred yards over there, which of those is better? And so we've tried to be very responsive to that. And I think that has been a very positive experience, and the local populations have been very supportive of what we've been doing. But it's just something to think about, that I don't think anytime soon you'll be able to just show up somewhere where at the nuclear reactor and just plunk it down. I think you have to do some thought. You got to make sure that the local community wants to buy in, that the local government wants to buy in, and that you've thought about the just all the little details about the local soil or earthquake risk or things like that, to make sure that you're still going to be safe no matter what.
Joe, there's a number of questions in the chat. So getting Pele, now getting Draco, potentially getting fission surface power. That is really exciting. But that's also a lot. And so when you look at that in terms of workforce development, in terms of your facilities, how do you manage having those multiple projects to try and either capture synergies or make sure that you can mitigate risk to be able to deliver multiple projects simultaneously?
That's a great question. And we had an early focus on heavy matrix staff, like I mentioned earlier. Now, with Project Pele in particular, that's what they're working on. So we have a large staff load that's been hyper-focused on all the design attributes, all the manufacturing development attributes. The fuel's being manufactured by another division of BWXT, but also here in town. So that was thing one. And then with the Draco build out, we've had staff working on NASA NTP for several years. So having them focused on NASA Draco, NASA and DARPA for the Draco program, consolidating that staff to focus has been really rewarding. And then we've been hiring, right? And we're hiring consistently. And we've doubled our staff count from about 15 months ago, and we'll continue to hire as needed. We've created a lot of momentum. And earlier this week, we had our send-off party for our interns. And even in my P&L, my business, we had 27 interns. So people understand, the realness of Pele, of now Draco. And so they're pretty interested in coming here for internships. So with those 27 interns, we will keep some of them part-time while they're finishing schooling, and we'll continue to hire those. So I would say our staff has come from a variety of different places. People like me have come from the Navy background, and then I had some high-tech background, and then we have a variety of engineers that are coming out of school, and really everything in between. So it's always a challenge, right? I think everybody's having this challenge in almost every industry, staffing up, but we've been able to collect a really amazing staff load, and we plan to continue to build that. In addition to that, we have other folks within the company that are helping on some staff aug type work. When we have these bumps and needs for FTEs, we can use them. And then we've been using really good staffing firms, and they've gotten a lot larger over the last couple of years for good reason. So all of that in between, everything that we've been doing is helping us meet the program objectives, and we'll continue to build out and partner and do things like that to make all these programs successful.
So when we look at Pele, it really kind of is a new generation reactor, but the Army has done a lot of work on transportable reactors before. In general, we did have the initial age of nuclear science and technology in the US, where we did learn a lot of lessons, developed a lot of things. How has this project been able to benefit from a lot of those legacy documentation, test studies? How much has it been incorporated? And I think especially now that we have a whole bunch of new advanced manufacturing techniques and other things, how have we been able to innovate on that legacy?
Yeah, so I view this in two different areas, which is the technology versus the regulations. And so from a technology perspective, the answer in what we've gotten from the Army nuclear of the past is nothing, basically. Those were very unsafe and crazy designs. And so we are not a technical descendant of those at all. That said, from a regulatory pathway, that's very different. The Army actually set up a very thorough regulatory body. There actually, when we started this, there was still an Army reactor office. It's actually still existed, even though the Army is down to one reactor. They have a research reactor in White Sands. But there is still, all these regulations are in place, the job titles, the training and everything. So instead of having to stand up a whole new regulatory arm from scratch, we're able to leverage the existing Army regulatory pathway. I think it's called AR 50-7, and just modify it to modernize it a bit and tweak it a bit to handle Pele. But the fact that we did not have to do that from scratch has been very helpful. So now there is not just an Army reactor office within a part of the Weapons of Mass Destruction division within the Army G357, but there's also a nuclear shop within the Chief of Engineers office within the Army Corps of Engineers. And so we work very closely with those two organizations, and I think it's been been very productive.
Joe, any thoughts on that as well, the legacy data and lessons learned?
Yeah, so I think Jeff hit it really well, especially with the Pele program. Space nuclear has been around for a long time as well. So pulling a lot of material science information, what they were aspiring to do when the programs were shut down, understanding all of the difficulties that they had and not revisiting those, not stubbing our toe twice as a country. So we do a lot of literature reviews to start off programs, and it's important for us to be able to use, to your other point, additive manufacturing and other advanced techniques, especially on the computational realm. That's evolving so fast. So how do you employ that with the need to just build things and touch things? So that's been helpful for us because we can evolve our products even faster, and we can use advanced technologies just to understand simple things like the type of fixtures that we need to build so we can manufacture and set up each one of these reactors and assemble each one of the reactors. And so we employ a variety of different additive manufacturing techniques, mostly to help us with the design, to help us with the integration, and maybe someday help us build an advanced or an additively manufactured reactor.
Yeah, actually, I was going to add one more thing about one of the interesting things about how back in the day there were kind of no rules is they were able to do all sorts of weird tests of what happens to this material in this weird environment. And so sometimes we want to understand, hey, what happens to this weird alloy or material in this very weird environment? The answer always ends up being that, 1957, some guy working on some kind of nuclear weapons program did this, and you got to call up these three people, and someone at Los Alamos will fax you something or who knows what. And so there's a lot of this weird old data that's actually very useful to us today. It's one of the fascinating things that's happened during this program.
So there's a number of questions I want to kind of group together in a way. And so when you actually look at the reactor, it's producing heat. Be interested in learning about how you're planning on converting that heat to electricity, what that means in terms of thermal efficiency, what that also means in terms of other applications of the reactor. And so is there opportunities to produce heat? Is there cogeneration opportunities, potentially produce hydrogen? When you're looking at the electrical applications, are we going to be able to use this for disaster response, emergency services, kind of going beyond just the traditional power reactor? Could you kind of maybe both go into a little bit of those additional applications?
Yeah, so the exhaust on Pele is hot air, literally. So you could use that for heat. We are not for Pele 1.0. We want to limit the number of miracles we have to achieve to get to success. But the precedent for here is that when the Army used nuclear power at Arctic installations in the 50s and 60s, they actually often used it more for heat than for power. So I do think that using nuclear power for both heat and also process heat for chemical processes, desalination, synthetic aviation fuel, I think those are all applications that the DoD is going to be looking at in the future. Joe, there might be some others that I wasn't thinking about.
No, I agree. And when we look at our Banner reactor, it's about cogen, right? So high temperature gas reactors in the microreactor format, they're not going to be cost competitive for grid scale power. So being able to utilize the thermal energy in addition to the electrical energy for a microreactor is going to be pretty crucial, I think, for the economics. So just like Jeff said, it's the Pele program is hyper focused on the program requirements, but as I see the technology evolving, especially getting into the commercial market, being able to use the excess thermal energy for other purposes it will be crucial just to get the deployment case to close from a financial standpoint.
And this question may be a little bit more directed towards Jeff, but across this whole conversation, I think that we've mentioned a bunch of different government agencies. DOE is doing the authorization, and NNSA is providing the fuel. NRC is collaborating. We've talked with all parts of DoD, Department of State, essentially the whole acronym soup of the federal government. Can you talk a little bit about some of those government engagements? Because it does seem like this is something that you've been a trailblazer in that area, and particularly how we're looking at having many different agencies involved in the nuclear complex going forward. What are some of the ways that we can navigate that world successfully like this project has done?
Yeah, that's a good question. That's pretty much what my day job is. Because I have people say to me, "Oh, it's so cool! You're building and designing a nuclear reactor. It must be fun." And I spend 0 minutes a week designing or building a nuclear reactor. There's other engineers who do that work, and so my day job is just communicating with all these agencies. I guess my advice for anyone else doing trying to do nuclear and selling it to the government is, do not think you can get away with not talking to these various agencies. And also do not think that just because you talk to one person at Department of Energy or NNSA that you've now talked to Department of Energy and NNSA. There are so many divisions I'm convinced that the NNSA just, replicates and creates new divisions all the time, because there's constantly new divisions reaching out that I didn't know existed. It's some kind of weird mitosis thing they have going over in that building. So it's complicated, but there's also good reasons for it, because sometimes they bring up things that you're not focused on, not thinking about. So you really just, as much as possible, need to get ahead of that and make sure that before you get too far down a pathway, that you talk to a State Department or these other regulatory bodies and just say, hey, this is what I'm thinking of doing. Is there a concern here? Is there a problem here? And we have tried as much as we can to be ahead of that, to do things like secure our uranium, to secure a regulatory pathway very, very early, so that we were not trying to deal with those things later, and any impact that might have had on design or anything like that. We want to try to get ahead of those. So that's really kind of my advice to any budding government program managers out there, to be ahead of those interagency engagements, not behind.
This question is for both of you, but I'm definitely interested in hearing from Joe first. When you look at developing this project overall, there's going to be a whole bunch of quality assurance, QC type requirements. We also are dealing with supply chain in the US that I think really there's been a lot of concerns that it has atrio feed that we've not necessarily had a lot of the nuclear grade suppliers we did in the past, and that's been a major barrier. Can you talk a little bit about those kind of interconnected issues in terms of making sure that we have a sustainable supply chain for things beyond just the nuclear fuel portions, as well as any of the QA or QC challenges that have emerged as part of this process?
Yeah, it just goes back into that's part of how we do business. And so even a few years ago when Pele kicked off, we knew we were going to have to get approved suppliers, right? It's all part of a nuclear QA program. So we have a staff from a QA and QC side that focus on those suppliers. They're performing a lot of local audits. They are integrating themselves with the design team and integrating themselves with the supply chain. So we've been able to port in a lot of techniques that we've been using for several decades, and we've developed more automated sequences because we'll have a lot more externally manufactured components. We'll be more assembly because of the timeline. So when I think about QA and QC, it has to be the frontline support on ensuring the suppliers know what's expected of them, right? It's also not fair, to your point, Alex, it's also not fair for each one of these suppliers that aren't used to the nuclear industry to expect them to flip a switch and be a nuclear grade supplier. So we spend a lot of time in educating them, and then bringing them to our facilities if we need to, and then talking them through the specific design details of Pele. So when they have to go off and make a component, they have all that background information, which is going to be valuable. So it's just a lot of effort, frankly, and I think that effort is starting to pay off, because as we're starting to receive components, or at least we're seeing some demonstration and factory acceptance tests and planning for all of that, we're getting a lot of the right feedback, of the right documentation, and then the right expertise in each one of those vendors. But it's gonna take the next several years as we go through building up the supply chain to make sure that's built up as strong as we possibly can.
And so we've got about 2 minutes left now. I do want to thank both of you for joining this. I think it's been a really educational webinar, and it's great to get the update. I think that I can speak for a lot of people saying that we're really rooting for this project, and we're excited to see it reach vision. I do have a final quick question though. Project Pele, where does the name Pele come from?
Sure. So my organization, the Strategic Capabilities Office, we are largely focused on China. We were stood up in 2012 to focus on China. We were focused on China before it was cool. Now everyone's focused on China. And as part of that, we have a cell of people out at INDOPACOM in Hawaii, embedded within the INDOPACOM J8. And so this program actually bubbled up from there. When I was hired to take on this program, I was handed a 2-page white paper laying out the idea of Project Pele and also the name Pele. Now, Pele was backronymed to Portable Energy for Lasting Effects, but no one uses the backronym. Pele is really just named after the Hawaiian goddess of fire and power. And I, for one, have always been a big fan of using mythology to name things. And so, for instance, the computer cluster that we've been using in Idaho has a name related to Pele. I'm not sure if I'm supposed to say what it is, so I won't say what it is, but we try to stick with mythological names. So that is where it comes from. It's the Hawaiian goddess.
Excellent. Well, thanks so much again for Jeff and Joe for you all joining us. And thanks everyone for attending. I hope this has been an educational webinar and we look forward to seeing you next time.
Thank you.
You.